Hello and welcome. This is Marwan Omar, and my presentation is Revolution Malware Detection, a paradigm shift through optimizing CNNs. I'm an associate professor of cybersecurity at the ITM department with Illinois Institute of Technology. So to begin, we know that cybercrime is a multi-billion-dollar industry, with malware being a prevalent threat. We hear about cyber attacks in the news all the time. So a lot of companies and business organizations are falling victims to cyber attacks for various reasons. We have conventional malware detection methods that are incapable of withstanding sophisticated attacks. So that's one of the challenges, is that traditional malware detection, such as antivirus, for example, is not capable to keep the pace with the new wave of malware, which is known to be sophisticated. The malware authors and writers are becoming more and more innovative and creative when they author malware. And this necessitates the advanced methods for effective cybersecurity. So because traditional cybersecurity methods such as antivirus, for example, is no longer effective, now there's a need for more advanced and more effective cybersecurity protection measures. So the problem here is that malware evolves rapidly, and therefore traditional detection methods cannot keep pace. There is a need for a model that detects stealthy and persistent malware. Here's the significance of the study that you conducted. Deep learning models, particularly CNNs or convolutional neural networks, they have shown promising results in improving detection rates, detecting malware, of course. And our study presents a unique model starting from the baseline to an enhanced version. So we start from a baseline, we continue to fine-tune our model until we get to an acceptable level of performance and detection rate for the model. So for original contributions, we have a novel CNN for highly precise malware detection. That's our goal, is to detect malware with high precision, high detection rate. This is a professional data science methodology used to incrementally build and optimize the model. So we build the model from scratch, and then we fine-tune it and we optimize it. The improved baseline accuracy is from 98 to 99.183. For literature review, we know that malware detection has employed machine learning with varied success. Our CNN approach is informed by past work and optimized for greater precision. For the system architecture, we have to convert malware binaries to grayscale images, and the classification of images into malware families based on textual features. So we know that convolutional neural networks, or CNNs, are a powerful deep learning model that are used in this section to categorize and identify image-based malware. So we treat malware as an image and classify whether it's malware or non-malware. The method, as we have shown, entails converting malware executables, such as Windows executables that are known to be malware, into grayscale images that are then divided into various malware families, such as botnet, banking trojans, backdoor, worm, and others. This procedure prepares our CNN model for the following feeding of the image-based malware classifier. So that's what we have. We have an image-based malware classifier, and here's the figure. If we zoom in here, So again, the conversion from binary to image process, and it demonstrates how binary executables are converted into visual graphics. According to the binary file size, the display graphics height varies. The CNN will analyze the pixel patterns in the image to predict the category or type of malware. First of all, it will try to detect whether or not it's malware, and then it will try to detect if it's malware. Then model will try to specify what kind of malware is it. Is it a worm? Is it a banking Trojan? Is it a botnet? Is it a worm or something else? And here's the visual architecture of CNN. And here is the convolutional visualization, as you can see here. We have the source pixel, the coordination kernel, and then the new pixel value. And here the center element of the kernel is placed over the source pixel. The source pixel is then replaced with a weighted sum of itself and the nearby pixels. So this is the process. And here is a table that shows us all the malware families that we are going to use to train our model. So you can see that there are 25 families starting with alpha L, alpha A, Uner, Lodia, all the way to Skintron. And the number of variants in each family. So we have 1591, 29, 2909, all the way down. So the total is 9,339. So the total number of samples is 9,313. So this is what we will use to build our model, to feed our model. So this is the size of the data set. So the size of this data set is 9,339 samples. And this is what we will use to feed to our model for training and evaluation. For the empirical results, so it seems to make sense to present and share the results after we evaluate our model. So we focused on the learning behavior of our CNN model before measuring its performance. The deep learning community is aware that overfitting and underfitting are two important issues that nearly every deep learning model faces: overfitting and underfitting. So in order to accomplish this and to ensure that our CNN model is not flawed with neither overfitting nor underfitting, we constructed a line plot to display and report the performance of our model on the test dataset as well as the trained dataset throughout each of the five-fold cross-validation. So we have cross-validation as well. The line plots will show whether our model is over or underfitted for the malware dataset. One figure with two subplots, and one for loss and one for accuracy of our CNN model, is all that is needed to comprehend the overfitting and underfitting difficulties. The training dataset performance of our model is represented by the blue line, while the how.test dataset performance is represented by the orange lines. So we have a code that accomplished this task, model performance, etc. And here we can see the cases where the model achieves perfect skill. These are good results. 98.467, 98.683, all the way to 98.583. The numbers above are impressive, and they clearly show that our model evaluation is progressing. So running the example generates the following results for each fold of the cross-validation. Cross-validation is an important aspect for building an optimized machine learning model. So we ended up getting 99.008. The pair-fold scores above may suggest some improvements over the baseline, as you can see. So for finalizing the model and making the predictions, we selected the final configuration of the CNN model. Despite the allure of making further advancements to our model, obviously, the deeper model will be our model's last iteration. Our model has been refined by being filtered to the whole we fitted it to the whole male MG training dataset. So that's the dataset that we saw in the previous slides with 9,339 samples. Male MG, that's the training dataset before being loaded and tested. On the holdout test male MG dataset, we will assess the performance and accuracy of our model. And this will allow us to see how our model performs on an actual malware dataset in terms of practical accuracy. On the test dataset, which is the malling, the model's classification accuracy is calculated and printed with a standard deviation of roughly 5%. We can see that the model in this instance attained an accuracy of 99.180 or little less than 1%, which is not terrible at all. So 99.18. And we can see here, we can take a look at more results here. And we can see here, if we scroll down, we can see more results. So this is again the data set, the training data set that you talked about. Here's the another diagram for the architecture of our CNN model. We have the convolutional layer one, reload layer, pooling layer, count layer two, reload, a hidden layer, reload, and the dropout layer. And this is the output layer with 25 families malware. So all images, as we mentioned for the dataset, are uniformly sized at 32 times 32 pixels. These are images, and they are presented in grayscale, as we mentioned. And consequently, the procedure involves loading the images and reshaping the data arrays to contain a single color channel. And the provided code snippet here exemplifies the approach that achieves this. So from curious.dataset, we type import load files. From Keras utilities, import NP utilities. Import numpy as NP. We will define the path to the dataset. Dataset path, path to dataset folder here. Then we load the dataset, which is the malware dataset family. Then we load the dataset here for training. We print the summary statistics, total training malware images, the length of training files, total test malware images, the length of test, and number of classes, which was 25 as you saw. We loaded the data set, and this process sets the foundation for further model deployment and evaluation using the malling data set. So again, the malling data set, as you mentioned, it has 9,339 samples from 25 families used for training and testing. So the importance of dataset diversity in training effective TNN model. We saw that our dataset had 25 different families. This is important, having a diversified data set, not just a data set that includes just viruses or worms or trojans or backdoors, but a variety of families like we mentioned, banking trojans, backdoors, worms, etc., etc. So as you mentioned, the establishment of the initial CNN model is as a baseline, and we assess the baseline performance to set the stage for enhancements. And then we started working on improving the baseline model. So we explored the model expansions to improve the learning capability, the learning rate, and then in the introduction of the complexity of the model structure for higher of adding more layer, making the model deeper and deeper so that we can get a higher accuracy rate. And then the initial model performance, so we use the performance metrics of the refined model to indicate a substantial improvement. The accuracy of classification for malware instances with 99.18 as we have mentioned. So the accuracy rate was 99.18 after training and testing. And so we had a detailed analysis. So you can look here for the analysis or the evaluation, as you had mentioned. So it seemed to make sense to present and share the results after evaluating the model. As you mentioned, we focused on the learning behavior of the CNN model before measuring its performance. As you mentioned, the deep learning community is aware that overfitting and underfitting are two important issues that nearly every deep learning model faces. And in order to accomplish this and ensure that our CNN model is not flawed with neither overfitting nor underfitting, we constructed the aligned plot to display and report the performance of our model on the test dataset as well as the trained dataset throughout each of the five-fold cross-validation. The line plots will show whether our model is over or underfitted for the malware dataset. So here's the code to create the plot. So the diagnostic plot is shown below, giving insight into the learning behavior of the model across each fold. As you can see here, the loss and accuracy learning curves for the baseline model during k-false cross-validation. The classification accuracy keeps going up, and the cross-entropy loss keeps going down. In this instance, we can observe that the train and test learning curves converge, indicating that the model generally obtains a good match. There are no overt or under fitting indicators. The performance of the model is then summarized. As you can see, the model in this instance has a reasonable estimated skill of 98.6. And finally, a box with whisker plot are created to summarize the distribution of accuracy scores. As you can see here, we may now look into a few approaches to enhance the CNN model, and in order to investigate enhancements over the basic model, we can alter the model's setup, changing the capability of the model's feature extraction component or altering the capability or functionality of the classifier component are two frequent strategies. These are two frequent strategies: feature extraction or the classifier. By adding more convolutional and foreign layers with the same size filter and more filters overall, We can deepen the feature extractor portion of the model in a manner akin to the VGG. In this instance, a second max pooling layer will be added after a double convolution layer with 64 filters each. And running the example generates the following results for each fold of the cross-validation process, which is 98.775, which is absolutely impressive. And therefore, finalizing the model, as you mentioned here, we explored again the model expansion to improve the learning capability and the introduction of complexity to the model structure, as you mentioned, adding more layer to the feature extraction capability or to the classifier capability. So we provide a detailed analysis of the model's learning behavior across cross-validation, and you presented the final model skills level through empirical evaluation, as you saw there. And as a conclusion and for future work, the study introduces a new standard in malware detection with deep learning. As you mentioned, CNN, building a CNN model from scratch and improving it, optimizing the CNN model. For future research, we will explore larger data sets and compare to other deep learning models. Obviously, the literature is filled with hundreds of studies and techniques that try to detect malware. And so our goal is to have more data sets and compare our model with other models that are similar in the literature. So again, this was for detecting malware using convolutional neural networks. As we had mentioned, malware evolved rapidly, and therefore traditional detection methods can't keep pace. There was a need for a model that detects stealthy and persistent malware. And of course, deep learning models, particularly CNN, have shown promise in improving detection rates, and our study presented a unique model starting from the baseline to an enhanced version. And these are some of the numbers that we obtained for the accuracy. As you can see here, 98.46, 98.68, 98.64, 98.85, 98.58, and these are more numbers: 98.775, 98.683, 98.967, 99.183, and 99.008. And again, for future work, we want to explore larger data sets because the data set that we had only had 9,339. We're looking for data sets with hundreds of thousands and more than actual one data set to generalize our model, to make sure that our model can generalize. So this is the end of the presentation. Thank you for your time and attention.